Okay. For those of you in section 500, and you know who you are, I just took attendance today. So if you're not showing up in class, send me an email, please. Okay. For those of you in the other section, remember there is no class tomorrow. Well, hi. Make yourself at home. Okay, so where we left off was really on sperm and egg production. How did you know we were taking attendance today?
You said it.
I was going to keep it as a secret. Okay. So where we left off was on mitosis. And I know you know mitosis and meiosis. And why bring up mitosis and meiosis? Because I think it's important to understand where it comes from and the crossing over. And that really, that the mitosis really is where we can find errors in cell division that lead to a lot of genetic abnormalities, as well as the issue that comes up in terms of why we're all different. If meiosis never occurred, we would be like lilies in Iran. Iran lilies really don't do meiosis the same way that humans do, so they can have maybe 400 or 500 chromosomes. We don't have that. So this is the importance in variation for us. And it is interesting in a sense that when we're interested in spermiogenesis or spermatogenesis, we start out with the primary, with the testes, obviously, start with the spermatogonium. We have a first meiotic division, then we develop spermatids, and they undergo maturation to develop into adult sperm. There's a whole science of sperm. It's called andrology. I know you never heard of andrology, but I happen to have a friend she's an andrologist, and there are in humans maybe 250 variations in sperm, and that can render issues with reproduction. So there are a lot of things that go on, and there are entire companies that do the analysis of sperm. Very important. In oogenesis, we start out with what we call a primary oocyte, and that undergoes division. Now, what you have to remember is we have a primary oocyte, that's 46N, and then we have around it a zona pellucida, it's protected. Then we can become additional follicles. So we go from what we call primary follicles. A female is born with about 400,000 primary follicles. Obviously, she doesn't ovulate that many, but they have about 400,000 follicles, and you develop what's called the primary oocyte. And then as the egg undergoes getting ready to become a mature follicle, because that oocyte will develop into mature follicles. So here we have the oocyte surrounded with fluid here called the antrum, which is very, very important. Now, at this point in time, what you really have to understand is it is at this time that we complete the first meiotic division. The eggs are held in meiotic arrest. At that point in time, we now can ovulate, and now when the sperm penetrates the egg, that's a signal for the second meiotic division. So, and the whole thing here is the polar bodies. The polar bodies are really just little bits of DNA. There's not much cytoplasm because we want to preserve the cytoplasm for the actual egg. Okay, so in fetal life we produce them. So essentially, we result in the germ cells that are essentially haploid. Okay, now, so in a fertilized egg, half the chromosomes come from the mother, half the chromosomes come from the father. In fertilization, years ago, When I showed you the picture of the sperm with the little person inside of it, bless you. If you remember, my daughter was reading one of those Anne Boleyn novels that are very popular. I don't know if you've ever read them. No? Okay. About Anne Boleyn. Oh, I got to recommend some to you. You know, she was executed by King Henry VIII, because she would not give birth to a male child. So he had to have a male child. So he had a couple of marriages. Then he got rid of the Catholic Church, developed his own church around him. So all of history based on this, that these women that he kept getting involved with could not deliver a male heir. So he cut their heads off. He blamed it on, of course, the females. But we now know it wasn't the woman's fault. The sex determination is really done by the Y chromosome or the X chromosome of the male. So that essentially he should have cut off his own head. But he didn't. So I think interesting historically that the lack of understanding about reproduction, we've always blamed, see, I'm defending you here, that we've always blamed the women because they haven't delivered a male child, when it's really essentially, it is the male's fault, because the sperm the sperm swim at different rates. You do know that we can isolate sperm because they swim at different rates. So we can isolate the male and the female sperm based on how fast they swim. And that's how we isolate them. I know it's kind of crazy, but whatever. Then sperm has to undergo development. So here we have a cell called the Sertoli cell, which gives the biochemical support and nutrition. And here are the spermatids, and they develop right here in the testes. And basically here we go from a primary spermatocyte to a secondary spermatocyte. It's meiosis 1. Meiosis 2 is when we form the spermatids. And we have to find nutrition for them. Now, sperm have a definite anatomy. They have a head. They're covered here by an acrosome cap. Okay? Then they have a middle piece here. They have a neck. And that neck has all the mitochondria. They need a lot of mitochondria. Then they have the tail. Every different organism, their sperm are not all identical. They're different. They're shaped differently in many different ways. Okay? And in the egg, essentially, we really deal with, at puberty, we take one primary oocyte, only one that completes meiosis 1 out of the 400,000. One completes meiosis 1. So we have the asymmetrical division, and then the secondary oocyte really arrests in metaphase 2. So metaphase 2 is when we stop this whole thing. And what we end up, as you know, is at one egg, 3 polar bodies. The importance is all the cytoplasm is right over here with the egg. The male we don't have to worry about. All they're bringing out is their DNA. Okay? Now, so here is our tail, a really close look at our sperm. So here is the nucleus covered by the acrosome cap. Here is the middle piece. Here's the neck. And here through it is the middle piece of the tail. Then we have the principal tail, and then we have the end of the tail. Not only do we do this, but in the male reproductive system, all the sperm are clumped together in what we call a coagulum. And that really inactivates the sperm. The sperm are destroyed in an acid environment. So in and around the sperm, we have vitamin C, we have buffer, we have thickening agent, all to protect the sperm. in the egg is surrounded by the nucleus here, the cytoplasm. We next have a zona pellucida, okay, and here is called the corona radiata. All rather important. So, just as a quick review, and I'll go through this here. Pregnancy lasts 38 to 40 weeks upon average. Day 1 is really the start. I think you know all of this, but so that we're all on the same page. Day 1 is the start of the menses, when we have desquamation and extravasation, which is ripping off the uterine wall and bleeding. On day 14, the egg is released from the ovary. On day 15, so I'm going to call this one day after ovulation, the sperm fertilizes the egg in the uterine tube. Why is this? Sperm do not live for a long period of time. They live for about 24 to 72 hours, and they get destroyed. We say this on day 1. That's very important for us, and I'll show you why in a moment. On day 24, which is 6 to 10 days after ovulation, the embryo, if you're pregnant, implants itself in the wall. On day 28 of the cycle is when most women would expect their next menses. Remember, depending on the time of the menses, it would be day 30. This would be day 30 in a 30-day cycle, and this would be day 16. So what I want to take a look at is the structure of what happens when pregnancy or pregnancy does not occur. So here is the menstruation. This is really day 0 here, when we rip off the upper 2/3 of the uterine wall. We have bleeding, and now under the influence of hormones, all right, we build up the wall of the uterus, and we increase glands, we increase blood circulation, we increase glandular structure right over here, anything to provide nutrition for if we're going to implant an egg. So the first phase of the menses is what we call the menstrual phase. Then we have the proliferative phase. Then we have the progesterone phase. And then here, if you're pregnant, we call it the gravid phase. On day 21 is here. That's when this is really maximum. And if you're not pregnant, you begin the desquamation process. Here you can see day 14 when we're releasing the eggs. So this is non-pregnant. Here is pregnant. If you do get a signal that you're pregnant, we'll speak about the corpus luteum that released the egg. In both cases becomes thicker, and thicker. And here, if you're not pregnant, the corpus luteum begins to degenerate. If you are pregnant, you begin to make estrogen and progesterone. Prior to fertilization, the cilia, there is cilia that move the egg towards the uterus. So essentially, the egg goes into the fimbriae, goes into that little glove we call the ostium, and we have contractions of the fallopian tube, and the cilia wave and move the oocyte down. The egg now releases chemical attractants, so the sperm know where to go. When sperm enter into the vaginal tract, the acid of the vaginal tract degenerates the coagulum. When we degenerate the coagulum, so the sperm are ejaculated as inactive, non-swimming entities, regardless of what Woody Allen movies say. They're just not active. And when they enter into the tract, we destroy the coagulum, and then the sperm become active. The sperm is still incapable of fertilizing an egg, because we need final maturation of the sperm, which we call capacitation. And that acrosome cap begins to become very fragile. That's maturation. So most of the sperm just never get to where they're going. They can go up one tube, they go up the other tube. Some sperms swim faster than the other, some are slower, some have wrong tails, some go backwards, some go in circles. They do all kinds of things. But very important, they are attracted to the egg. They're attracted by the chemical attraction. They're also attracted during orgasm. The uterine tubes contract to aid the sperm to reach the egg, and the female has strands of mucus produced by mucus glands. We're coming back to mucus glands. Strands of mucus gland that act as a guide for the sperm. So, upper third, we have to get the egg and the sperm together. All this really is leading up to what we call pre-implantation. This is really kind of important as we've got to do this. Now, I just want to go backwards here for a moment and cover something here. We're ultimately, if we're pregnant, what happens is when we have fertilization, we release a hormone called HCG, human chorionic gonadotrophin. I have it a little bit further up, but it's worthwhile mentioning now. Human chorionic gonadotrophin is what we're measuring when we do those pregnancy tests. That's the chemical. What HCG says whether you're pregnant or not pregnant. And that is the signal to the body. Now, what's going to happen is on about day 21, and we're going to go through this again, so I'll mention it. If you're pregnant, HCG sends a signal to produce progesterone, and progesterone and estrogen maintain the height of the uterine walls. Ovulation on day 14 is stimulated by LH. But day 21 is very, very important. And again, we'll go through that again. If the signal is that you are not pregnant, okay, the lack of HCG causes a decrease in progesterone that causes lack of support for the uterine tube, that now for the uterine wall, and at that point we undergo desquamation. So that is very, very important, that progesterone signal, okay? When the egg is released, although the sperm may be viable for 72 hours or less, the egg is viable in the tract for only 24 hours. So years ago, we used to teach that when a woman ovulates, if we start to get the sperm on the way to the egg, that is a good sign for getting pregnant. We always taught that. Every biology class taught that. But the data is a little bit different. The sperm really has to be there before ovulation, because it could take a while for the sperm to get there. All right? So when they do the data, much to everyone's shock, all right, is that if the sperm arrived late, less than the zero, the way they planned it out, there's almost a 0 chance of getting pregnant. So the sperm really has to be available kind of quickly because of the viability of the egg. All right? So the sperm swim, lots of in that coagulum that is in the ejaculate, we have prostaglandins that stimulates the uterus to the fallopian tubes to contract as well. And then again, this is what happens. So essentially now, the sperm has to meet the egg. And here's a picture of the sperm meeting the egg. All right? What now has to happen is the egg really is held in meiotic arrest, and we've got to get the nucleus of the sperm, which we're calling a pronucleus, to the nucleus of the female. Okay? That's very quick. So here is the male. One sperm enters. The nucleus starts traveling to the nucleus of the female, and this is occurring while meiosis II is going on. So here is the sperm binding to a receptor called ZP3. At that point in time, we're going to develop the acrosome reaction. And this is a question. So when the sperm cap becomes fragile and the sperm is reaching to the egg, we essentially have digestive enzymes that lets the sperm digest away the zona pellucida. And if we digest away the zona pellucida, the sperm nucleus now enters into the cell. There it is, the sperm with the tail goes in. We don't care. At that point in time, we want to make sure a number of things occur. We want to fuse the egg and sperm membrane, okay? Now we want to make sure that another sperm does not penetrate the egg. And when the sperm penetrates the egg, we immediately have a depolarization. So sodium ions come in so that we depolarize the egg. We call that the fast block that occurs very, very quickly. And that increases calcium as well. Then we develop a cortical reaction, and that is the slow block to polyspermy. That is within 30 seconds. Once the sperm penetrates, we have a signal to speed up the ovum, and within 30 minutes after sperm penetration, there is a second meiotic division. So here we go. The sperm come along here. We digest away an acrosomal reaction. We fuse the membrane. We have a fast block, the sodium, within a few seconds. Then the cortical reaction, which really deals with release of calcium ion. When we release calcium ion, that hardens the zona pellucida so that no other sperm can penetrate. That is a picture of a sperm penetrating an egg. Yes, it's human. Leave me alone. Here is the membrane. There is an egg that's been fertilized. And here I just show you the two nuclei that are going to start migrating to each other. Okay? So when I taught general biology, and we include plants in that, I know you don't want to hear it because we're only dealing with human. We say that in plants, we require a double fertilization. Well, guess what? In you, if we're going to call fertilization, historically we say fertilization is the sperm penetrates the egg. But when the sperm penetrates the egg, that doesn't mean that you're pregnant. That doesn't mean we have a zygote. It means that we must then have the nuclei meet. That, for me, okay, from evolution of plants, we never came there. You can yell at me, I don't care. But evidently, that could be almost, in my mind, like a second fertilization. But you don't have any development if that doesn't occur. They got to go together. There's another picture of that. We dump out the second polar body because that's useless, right? And what we again need is all the energy, because this is the nutrition for the egg until we can implant. That's 7 days of stuff we have to have. That's important. So, got mixed up here. So I'm going to come back to the umbilical cord. But ultimately, what we're going to develop is an umbilical cord. We have two arteries that we'll show you later that carry blood to the placenta, and one umbilical vein that carries blood to the fetus. It's all mucous connective tissue, just to let you know. All right? After you're born, the umbilical cord can drop off, and you have a scar. And that scar is your umbilicus, your belly button. Just as a warning, we're going to speak about implantation. We're also going to speak about developing the placenta. All right? When we develop the placenta, sometimes there's that placenta can implant itself near the covering of the Oz, which is the opening to the cervix. And that occurs at I would say a relatively decent ratio, 1 to 250 live births, which can lead to premature birth, increased maternal mortality, and spontaneous abortion. So usually in the 3rd trimester, a female may see bright red vaginal bleeding, and then we try to do a C-section fairly quickly. Again, we use sonography. I still have my kids' pictures. They're not hanging because that's embarrassing, but we want to see where the fetus is. And we want to take a look at position, we want to take a look at viability, and yes, some people are even interested in finding out the sex of the baby so they know what color to paint the bedroom or whatever. One of the things that we'll speak about is how do you know if the baby is normal or problems? Usually, as I told you the other day, that we usually measure different chemicals like alpha-fetoprotein. And by the way, just to let you know, although when you take a urine test to see if you're pregnant and you get all the colors changed, that is not, again, sign that you may be pregnant. There are things called false positives. So the best way, you can wait 9 months and see if you deliver the baby, but if you want to do something else, there are blood tests that are much more accurate. And that's what a physician would use. If you get an abnormality at 14 to 16 weeks, you could do an amniocentesis. It takes approximately 4 weeks for the results to come in. But when you do an amnio, this is why we like the alpha-fetoprotein, which has no risk of abortion. The amniocentesis has its own inherent risk of spontaneous abortion, although it's about 0.5%, which is relatively low. But easy for me to speak because it is relatively low, but it does occur. The problem with amniocentesis is that if you decide to do amnio, it takes 4 weeks to get results. During that 4 weeks, remember, you test that you can't test an amnio before 14 to 16 weeks, which is for a 12, like 3 months. And you take another month to get results. All right? So the problem with amnio is that if there's a problem, then you have to make a decision. People want to make a decision whether or not to do abortion if there's something wrong. I'm not saying abortion is whatever. This is a very painful period for people. When my wife and I, as I said this, were pregnant, one of our children, we had an abnormal alpha-fetoprotein level, so we decided to do amnio. It was the most incredible period of time in our lives because all this time I said, choice, 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 choice. Everyone has choice. My wife and I were talking, what would we do? And that really is the problem. So I'm not going to tell you what we decided, but you know, some people choice, and ours was no choice. But that's not. I'm not going to go into the politics, but that's a problem with amnio. So then you have CVS, which is not the food chain. It's chorionic villi trophin, chorionic villi sampling. In chorionic villi sampling, you can go in as early as 8 weeks, and you can have a result very, very quickly. And what we go into the chorion and take tissue samples, and we can know whether or not there's an open neural tube defect or some other defect quickly. But however, so here is amnio, here is going in with chorionic sampling. The problem with this is that we take some small piece of placenta through the abdomen, and then we can do the character analysis But this way takes 5 to 6 days, 8 days at most. But the chance of a spontaneous abortion rises from 0.5% to 1. I put down 1 to 2, it could be 2.5%, but the risk is much greater. But earlier, it really depends. There are hormones of pregnancy. There's from the chorion, as we'll explain, from day 8 to 14 months, we make human chorionic gonadotrophin, which keeps the corpus luteum active. After that, we develop the placenta. So we develop progesterone and estrogen to maintain the lining of the uterus. Remember, that's key for uterine thickness. If you lose it, you desquamate. The placenta is in the 4th month. The placenta alone will produce progesterone and estrogen. So we don't care about that corpus luteum. We also release something called relaxin. There are a couple of hormones. So that will relax the connective tissue of the pelvis and the cervix. And what relaxin does in the symphysis pubis, it will soften it up so that we can stretch the pelvis. And by the way, you can overstretch that symphysis pubis and wreck it. And that usually requires a C-section afterwards. But in wreck it, then they really have to do physical therapy. I can go into that too. All right. So in the placenta, we also make something called human chorionic somatotrophin, which is essentially the hormone that's really involved in maintaining progesterone and estrogen. We also have lactogen that prepares the mammary glands for breastfeeding. All right? And we also have something which we never mentioned to you in A&P, I guess, if we did or didn't. We release something called corticotrophin releasing hormone from the anterior pituitary. That's very important because cortisol is an absolutely vital, important entity for maturation of the lung. So that's key. And it is cortisone that determines the timing of birth. Kind of interesting. So we secrete all these compounds so that birth is decided by cortisone. And that the placenta takes care of that. We release the somatotrophin that prepares the mammary glands, increases protein synthesis, as you can see. And very important is that we want to develop fatty acids for ATP production, which is very important. Okay, so I'm just telling you, false negatives, false positives are very important. The false negatives are probably very serious because persons say, I'm not pregnant, and then go out on a binge, and then the false. That's why we always say it's very important. Please, if you're a person who's taking hormone therapy, if you're taking steroids, if you're taking thyroid hormone, if you're taking diuretics for hypertension or whatever reason, that will give you false results on pregnancy tests. In terms of twins, that's basically 2 oocytes, fraternal twins, fertilized by 2 separate sperm. And then you have identical twins in which you have 2 individuals from 1 ovum. They're always the same sex. Fraternal twins don't have to be the same sex. So, with that diversion, we're coming back here to the penetration of the sperm into the egg. Here are the pronuclei. Here is the egg pronucleus. At that point in time, they meet, and we're going to start. There's the fusion. That fusion now says you're a zygote and you have a diploid number of chromosomes. And right away, you begin the process of mitosis. 1 cell, 2 cells. We undergo a very rapid mitotic division, and each cell we call a blastomere. So that's the term I'm going to use for the next few minutes. We then go into a 2-cell stage, a 4-cell stage. The first cleavage takes 24 hours. Okay? Second cleavage is on day 2. By day 4, we have a solid ball of cells within 96 hours called a morula. So there's your cleavage, 2, 4, 8. 8, 16. We have a solid ball of cells. Now, the cells continue to divide, and the next stage is what we have a blastocyst. So here is 2, 4, 8 morula, and as the cell divides, this is very important, we have a cavity here called the blastocyst. You see that? Got that? You see this? That outside layer of cells, that's called the trophoblast. That's going to start to lead to implantation. You see this here? That's going to be the baby. That's your inner cell mass. We'll explain what they are in a second. That inner cell mass will become the fetus. So the blastocyst is a hollow ball that enters the uterine cavity really on day 5. So now, this has now traveled down. This is occurring while the egg is traveling down the uterus. On day 5, it now enters, it's coming down the uterine tube, fallopian tubes. On day 5, it enters into the uterus. And what we see is this inner cell mass. We see an outside. So what we'll tell you is that the trophoblast and part of the inner cell mass will become the placenta. At least what the fetus, the embryo contributes to the placenta. Can't speak. So here I want to show you what it looks like in real life. These are real eggs. This is the trophoblast, the blastocyst, and the inner cell mass. Isn't that fascinating? So here is our inner cell mass that some people call the embryoblast. It will become the embryo. This space will become what we call the yolk sac. And within a few days, we're going to see cells in here that are primitive red blood cells. Red blood cells develop early. They don't look like the rest of you here. So again, here's a traveling down. Fertilization, 2, 4, morula, day 5, we're right over here. We mature a little bit, like on day 6, we have the inner cell mass and really the trophoblast. This occurs within 6 to 7 days. Okay? Just showing you the pictures. Okay? Now, what terms we're going to use, we're going to speak about induction. One cell, 2 cells together are kind of interesting, but it's as if one cell tells the other cell, if you become this, I become this. By the way, when I look at this, 2 cells are the same, 4 cells are the same, 8 cells are the same, and when I look at this, I know this will become the brain, this will become the lids, this will become the heart. I already know what cells are destined to become what early on. So we deal with the concept of induction. Cells communicate to each other to lead to development. We have a term that I use all the time called morphogenesis. That's what we use to become specific tissues. Now cells migrate. So we have something called neural crest cells that we're going to see. They migrate and they become part of the brain and they become something that will lead to what we call enamel. Very early on. We differentiate, we specialize, and we grow within to get larger. Okay. This is the entire process. Here we have day 7 is implantation. And here, and you can see that we're really developing, and I'll go through these stages, into the uterus. And you can see why we need the uterus so thick. We need glands, we need vascular supply, we need everything here. So here is our blastocyst cavity. Now, what's going to happen, we have two called the bilaminar disc. I showed this a number of times. Here's the yolk sac. Okay? Keep that in mind. And we begin to, this cell mass here begins to separate from the trophoblast. And this will become the amniotic fluid. Okay? The outer layer is the trophoblast. Okay? And this will develop into the embryo. We now are going to go into something called gastrulation, and we're going to develop something we call a primitive streak, which I'll show you. But when we develop the gastrulation, we begin to develop the mesoderm. And right here, this will develop the ectoderm. This is the mesoderm. And part of this will become the endoderm. Very quickly. So I love these old pictures. So here are the normal sites of implantation. If it's out of this area, it's usually problematical. So on day 7, the blastocyst will stick to anywhere on day 7, the blastocyst, wherever it is, once it hits the wall, will stick to the wall. 6 days after fertilization, 7 days after ovulation. It is the side with the inner cell mass that is contact. It's not random. So this part here, okay, that is going to be very, very important for us. The inner cell mass is in contact with the endometrium. The trophoblast becomes 2 cell layers. It becomes a syncytiotrophoblast that digests away the wall. That's a good question. And the cytotrophoblast will decide the shape of the embryo. The trophoblast, once again we implant, it starts to secrete HCG. So basically, within 7 days after fertilization, HCG is, it has to, we need, so if we ovulate on day 14, we implant on day 21, all right? We release the HCG, that decides we're pregnant. We now have 7 days to decide pregnancy or not, or desquamate and get rid of the tissue. That's why from day 14 to 28 is sacrosanct. Because on day 21, with implantation, that's when we secrete HCG. And that will maintain it. No HCG on day 21, no, you're not pregnant. So here are pictures. So here is the inner cell mass. Remember I told you. Now the inner cell mass starts to digest away. There's the cytotrophoblast. There's the syncytiotrophoblast. Here's the amniotic cavity. And this is the cell mass. We're now going to call that names. Okay? So we have the inner cell mass. We're now penetrating. And notice how we're digesting away the walls of the uterus. However, remember I said that the blastocyst will implant on day 7, wherever it is. And this is key, if the egg does not come down fast enough, or it slows down, it will implant in the uterine wall, and that's called an ectopic pregnancy. All right? And that could be for many reasons. You can have inflammatory disease, you can have endometriosis, all kinds of things. By the way, in smoking, we speak about this in the respiratory system. We say that if you smoke, the cilia in the pseudostratified ciliated epithelium do not beat as rapidly, so you have trouble getting up the mucus. What you may not realize in smoking, because when you smoke, it's not only the tar, it's the nicotine. That elevated level of nicotine is what paralyzes the cilia. So if it enters into the vascular system, okay, it will paralyze the cilia. So the egg doesn't move down with its speed, and we see that the number of ectopic pregnancies is statistically higher in smoking women because of the nicotine. Okay? Now, once we implant, we cannot call this an inner cell mass anymore because it has two layers. It has the layer over here called the epiblast, and in yellow here, obviously it's not colored yellow in the human, it's called a hypoblast. Epiblast, hypoblast. Epiblast facing the inside, hypoblast facing the outside. There is a trophoblast going in. Here are the glands. Incredible. So now we have our lamellar disc. Here's the amnion. I'm repeating this over and over again. There's the epiblast. There's the hypoblast. Okay? We call this the bilamellar disc. On day 8, we're ready to have dug in, and we're nearly implanted. Nearly. All right? Now, and when I said 8 days, we're nearly implanted. We now are digesting away the uterine walls. And right over here, you see that? On day 9, because we've dug a hole here, all right, we don't want any bacterial or infectious agent to come in. So once we have total implantation, we put a plug over there, and that's called the coagulation plug. So now we're in a really great environment. And we form now from the hypoblast, right there, we form a membrane going around the entire trophoblast here, and that's called Hauser's membrane. Hauser's membrane, coagulation plug. On day 10, we have the yolk sac, we have the epiblast, we have the hypoblast. Okay. So this is just repeat. On day 14, that's the day that we begin gastrulation. We are going to form 3 germ layers. The endoderm forms the epithelial lining of the GI and respiratory tract. The mesoderm will form bone, muscle, and other connective tissue, and parts of the teeth. And the ectoderm will develop epidermis of the skin and the nervous system, and will lead to the development of enamel. I'm separating enamel from the other tissues here. So we have the yolk sac where blood cells are made, and these are where we're going to make either the eggs or the sperm of the future fetus. We have the amnion, which surrounds the embryo with fluid. That is a shock absorber, because the function of the amniotic fluid as fluid is to have viscosity so that the fetus is not bounced around too much. It is the amnion and the amniotic fluid that helps maintain the body temperature of the developing embryo. And in the amnion, the fluid is made up of filtrate of the blood, and it's also, because the fetus is going to urinate as the kidneys develop, the amniotic fluid is also made up of fetal urine. Urine is sterile. Just letting you know. The chorion becomes the embryonic placenta, and that's from the trophoblast. And the allantois, which I'm going to show you as part of the yolk sac, will develop into the umbilical cord. So here is, by the way, that's the fetus, that's the heart, that's the tail, that's the yolk sac. Okay? Okay. I just repeated this because we're about to train.
We said the yolk sac.
What?
We said the yolk sac was the fluid, right?
The yolk sac, the amnion is this. That's the amniotic fluid. The yolk sac will become where we develop the first blood cells. We need blood. We can't, if we don't have blood cells, we don't develop a heart. And if you don't have the yolk sac, it also provides nutrition. If you don't have the yolk sac, you won't make sperm or eggs in the fetus. We start that early. Okay. Okay. All right. We repeat that over. So it's a day here. Okay. Now this is what's going to happen. We have a process called gastrulation. It begins really to form 3 germ layers. All right? We form something called, and I have a number of diagrams here trying to explain this to you. In week 3, we develop really this thing called the primitive streak. This occurs on the epiblast. So I'm going to describe, I always try to find diagrams here. But here is the primitive streak that develops. It starts in the epiblast, and the epiblast starts to grow. And really here, this primitive streak will decide whether the right and left sides of the embryo. Okay? The epiblast will form the ectoderm. All right. Now we already know from looking at this that this will be the head and this will be the tail. How do I know? Let's take a look. So take a look at this. What I'm going to ask you to do is imagine opening up a container of cream cheese. Okay? Now, you're going to do what I do, all right, which is very important. You're going to do what I do and not what my wife tells me to do. My wife tells me to take a knife and put it into the cream cheese. Correct? Not me. Because what I do is I stick my finger into the cream cheese, draw it along the top. Can you imagine that? You know what that looks like? Can you imagine that? Yes? That is what the primitive streak looks like. Now the best part is that when you're going zipping down, you zip down and you always have like the tail, so my wife always knows that I'm guilty, and you have over here against your finger, you have a little buildup of cream cheese. Got that? That's going to be the brain. That's going to form the teeth. You will never eat cream cheese again without me going like, zoom. Got that? That's what that is. That's what it looks like. Now, you can't see this on the recording, but I'm going to show this to you now, and we'll go through it again. Here's my right hand, fingers extended. Here's my left hand, fingers extended. And they meet, right? You see that? You got that? Everyone see that? This is the epiblast. Underneath here somewhere is the hypoblast. Watch what happens. Ready? The cells grow in like this. They curve around. You see that? You see where my fingers are? Congratulations, we just made mesoderm. How easy that is? Whoops. Mesoderm. So it's forget what you read. I'll just be like, whatever. It just comes in. That is gastrulation. Now, to add to your total confusion, although I said the hypoblast is really part of the endoderm, migrating cells here will also form the endoderm. You know, some cells will migrate down, and that will form the endoderm. So we have the mesoderm, some cells migrate down, and it will replace the hypoblast. But for us, hypoblast is good enough, but we ultimately will replace it. So there is this, and the cells grow right in. Not only are they going inward, as you can see, this is also, so now imagine when I go into the cream cheese, I go halfway down from the end to the middle. You got that? I look around, and the next day my wife is yelling at me. She says, "Who did this?" And I'll say, you know, Sadie, who's the dog, but she doesn't believe that either. Or it could be my cat who's got Alzheimer's, but she doesn't believe me either. And then what I'll do is I really feel irritated. I'll put my finger in that and extend it all the way over because I can. You have that vision now? That is what this is. That is this. Whoa. That is these cells moving over here. We've extended all the way across. So in gastrulation, we move up this way. You with me here? That's where my finger is, right there. You want me to draw my finger in? Whoops. So here is my finger. And I've zipped it all the way along here. So now my finger is over here. So as I move in this direction, the cells are moving in that direction. This is the cloacal membrane that will become your anus. This right here, you see that little circle? That will become the oropharyngeal membrane. We're going to show you how that becomes the membrane. That's going to be your mouth. Got it? So here we have the cells growing in, forming the mesoderm. Here's the hypodermis, may be replaced by other cells to become. So in the trilaminar disc, ectoderm, nervous system, epithelium of the eye, ear, and nose, hair, nails, mammary and cutaneous glands, the epithelium that will become your oral and nasal cavity. It will become your intraoral glands, everything in here. In the mesoderm, the muscles, bone, cartilage, blood, dentin, pulp, cementum, and the periodontal ligament are all mesodermal. Ectodermal are, of course, the enamel from neural crest. And I can prove this because we can grow teeth. Easy to grow teeth. And I'll show you what the problem is in humans. And here's the endoderm. The what? No, an enamel. That's the ectoderm. You just killed all of dentistry in one sentence. All right? So here's the breakdown of what it all becomes. Very important in what we do. And take a look right over here. What does that say? Tooth enamel. So here is the picture of gastrulation. If you can't envision it from my lousy description of my hands, so here we go in, is the cells come in, and we're going to replace the hypodermis with true endoderm in time. So here is the movement. Up here, the epiblast. This primitive streak will move up. Up there is what we call the neural crest. So that's gastrulation. So basically, it's every, and I'll cut this out. What we have to do is that ultimately, we will develop into what we call somites. And let's take a break here.